Hello everyone. In today's lecture, I am going to talk about LCD and keyboard parallel interfaces. So in embedded systems, or with any type of microcontroller systems, sometimes we need to get some interaction or some outputs from the AVR that is performing some operations, so we need to see exactly what's going on. The one way of doing this is using LEDs. So we can use LEDs, we can turn on and off, and we can understand that something is happening inside of the embedded system. Another output type is the 7-segment LEDs, which we can display 5 characters on it. And the most comprehensive one is the LCDs. LCD displays, they can display the numbers, the characters, and graphics as well. So they're more capable compared to the 7-segment displays, and they're more preferable to use in embedded system to inform the user. So in this chapter we are going to see what is LCDs actually, how it is made based on the structure of the LCD, and how we can use that structure with AVR to program it, to interface it. And we are going to see how we can configure the AVR or the commands that we need to send, and we'll do a simple example as well. Then we'll touch a little bit on the keyboard interfaces, so for an input with a keyboard, how it is made, and the switching or the buttons, bouncing and debouncing topic will also be covered in this chapter. So let's give a start, and let's start with the LCDs. Now, as we already said, LCDs are used to inform the user for something in embedded systems, and they're made up of liquid crystal, so that's why they are known as liquid crystal display. And as you can see from the figure, we have got two plane of electrodes, the front and the back, and we have got the liquid crystal in between them. So on both sides we have got the polarizers, and they reflector mirror on one side. So what is actually happening over there when a AC signal is applied, where the electrodes are already selected, it aligns the liquid crystal molecules by creating an electrostatic field. And these crystals are allowing light to go through when aligned in the selected regions. You can find more details about LCDs, but I'm not going to go into the details because we are more interested in how we are going to interface it. So LCDs generally have got a matrix, and these matrices are, we have got the rows and the columns, and when we place dots on those and the rows and the columns, we can actually create a character. So as you can see from the figure over here, we have got an arrow. So by placing these dots in different places on the matrix, we can create different types of characters. So liquid crystal displays, as I already said at the beginning, they are more capable compared to the 7-segment displays or the ordinary LED notifications, because LEDs are just for 1 bits, 7 segments are limited with the characters, but with the LCDs we can display numbers, characters, and the graphics as well. So that's why we prefer to use LCDs in embedded systems for any kind of notification. And one of the most commonly used LCD is the 16:2 character line LCDs. So we have got 2 rows and 60 characters that we can write on it. So this is the typical one that we have. You can see out the pin diagram over here. We have got 8 data bits. We have got a couple of control bits, right, register select, read, write, or enable, and power source and the anode cathode pins. And we are going to see how these each of these pins are interfaced with AVR in the next following section. So RS pin, which is one of the control bits, is the register select. LCDs are working in 2 modes. Either we have the command, which controls the LCD display, or we have the data, which we write on the LCD display. So, and each of these functions have their own registers. We have got the data register, and we also have the command register. So from the AVR side, we have to specify which register we need to use. So if we want to we want to control the LCD, we have to write on the command register to be selected, which is RS should be equal to 0. Or if you want to write something on the LCD, we have to select the data register, which is RS needs to be set to 1. The other pin that we are interested in is the read-write. So generally, if you want to perform some operation on LCD, we use the write mode, because we want to write something on LCD or we want to change the command. Again, we use the write function over there. For reading, you can read the status of LCD if you want, but generally RV is set to 0 for writing data on it. Enable or E pin is when we want to supply the data through the data pins, we have to enable the latches on the LCD. So for that enable, we just need a short amount of time there, which is like a 450 nanoseconds wide, so that we go high to low for a short amount of time. We enable the latch. That means we transfer the data, we make the latches transparent, and we transfer the data. So these are the three important bits that we need to use when we want to configure LCD interface. Now, inside of the LCD, we have 4 important components: the data register, the command register, the character generator RAM, and data display RAM. So if you want to write something onto LCD display, we first put that value into the data register. Then that value will be copied into the data display RAM. And we also have the cursor over there. Each of these locations are actually representing 1 pixel on the LCD screen. So when we put the value over here, and that will be transferred to the data display RAM, it's going to appear, for example, hex 80 will be the first pixel. Let's say we have a character G, and that will appear on the first bit or the first pixel on the screen. Now, at the same time, if you want to configure your LCD to do some functions over there, like we can clear the screen, return home, increment the cursor, decrement the cursor, shift display, display on, off. So there are different types of functions that we can do on LCD as well. For those functions, we need to use the command register. So that command register will have the value, which we are going to see in a minute, the table for those commands will have that value, and it will configure the LCD to be performing that function. Then we also have the character generator RAM. Character generator RAM, if you want to have a different types of fonts or the characters, we can use this character generator RAM, which we are going to see that in a couple of slides as well, and we can edit the characters and we can modify it, and we can have our own characters in there. So character generator RAM is actually 64 by 8 with RAM, so it's actually 64 bytes. And data display RAM is 128 by 8, so it's 128 bytes of RAM. And this contains the data that has to be displayed on the LCD, and this is having the characters which we are going to store it. So different LCDs might have a different CG RAM. Some of them are storing 8 characters, some of them are storing 4 characters or 10 characters, and so on. Another important thing over here is the cursor. So cursor is like our program counter in AVR. So when you write something over there, the cursor moves to the next location and it's ready to write something on there. Or you can use some of these commands and you can skip some of these pixels, right to left or down to up, and you can modify the characters on that LCD as well. So we already provided details over here and also here. So data register is an 8-bit register, And as we already said, if you want to write something onto the data display RAM, we first need to put it into the data register. And the command register, if you want to configure the LCD, we use the command register. So data bits are 8 pins data bits we have got. But sometimes if you have a limited number of pins on AVR, we can also configure LCD to just use 4 bits of the data. In the command section, I will show you that as well, in the examples as well. So we can actually send information to LCD, we can read the internal LCD registers, and we can display the characters on LCD. And as we already said, for the command register, we have got specific values for those commands. For example, clear display has to be hex 1, return home is hex 2, decrement cursor, hex 4, hex 6, and it goes like that. So for example, if you want to configure your LCD to be an 8-bit, we can use the 8-bit data lines, we need to write hex 38. But if you want to use 4 bits, we need to write hex 28. And you can use that table to configure it for different purposes. So for example, if you want to write something on the LCD, there is an example given over here with 50 hex. And 50 hex, first, it has to be stored in the data register. So we write the hex 50 into the data register, then that will be copied into the data display RAM. And once we got it in the data display RAM, it's actually appearing in hex 80 location, where the hex 50 is P, and we'll see P on LCD screen. Then what will happen? The cursor will move down to hex 81, and it carries on like that. So the LCD commands, we can use these LCD commands to, at the beginning, for example, we can clear the display. We can say that, okay, when we have the new character, shift the cursor right. We can turn off the display, turn on the cursor, blink the cursor, and so on. You can use these functions again based on your needs. So for example, to clear the display, we just write hex 1 into the command register. This will clear the display. Return home, hex 2. Display and the cursor, for example, display is on, the cursor is blinking, 0 hex F or 0E hex or 0CH. So 0C hex is actually display is on, the cursor is off, and hex A is actually to display is off, cursor is off, so we cannot see anything over there. And as we already said, if we go back from the data display RAM, each of these location is actually represents one pixel on that LCD screen. So you can see that over here actually. So this is like a 4 line by 20 characters, and each of these is represented with one location in the data display RAM. And the one that we are generally using is 16 by 2 LCD. That's how the formation is happening over there. So line 2 starting with hex 80, and line 1 start with hex 80, and line 2 start with C0 and goes up to 16 characters. So for example, if you want to display a character in line 4 column 1 of 20 by 4 LCD, so line 4 column 1 is D4. So what we need to do, we have to write this into as a command, so we can move the cursor to D4 location or D4 pixel. So that means D4 is going to be highlighted. That means we need to write D4 hex into the command register, and we can move the cursor down there, and we can start writing something in it. Also, we can increase and decrease the cursor, which we can use 4H or 6H command. We can shift cursor to the right, shift cursor to the left, and so on. And you can see the couple of examples here. Increment the cursor with the direction to the right, or decrementing the cursor with direction to the left. And these are all acceptable ways of using the LCD commands. So now we know the LCD structure, how are we going to interface with AVR? That's the most important part in this chapter. In LCD programming, we have got 3 steps. One of them is LCD initialization. The second one is sending commands. So we have to configure LCD before we send any data to it. And the third step is to send the data. So I'm just going to summarize these on the whiteboard, and I hope it will be more clear. So let's say sending commands and data to LCD. Now, the first thing to do, we need to initialize the LCD. So how do we initialize LCD? To initialize an LCD, we need a couple of commands. So for example, if I go back to the command table, I'll show it from here. First, we need to say that, okay, we have got 2 lines, 5 to 7 font and 8-bit data length. If we are going to use 8-bit, we have to set that to 0 hex 38. That means this is going to be the first instruction that we are going to send. We are going to use 8-bit data length with 2 lines and 5 to 7 font. So that's the first step. Then the second command that we need to send is, okay, it has to be display on. Do you want the cursor blinking or off or on? So I'll suggest you to use, it's up to you again, but I'll prefer to use the cursor on, which is 0E. So I can see the cursor next to my characters. And another command that might be interesting to use is the clear display. So what I can do, before I write anything else over there, I refresh my screen, I have an empty screen, and I'm ready to write something on it. And one more command, which is again optional, this one. After displaying a character on the LCD, shift cursor to the right. So we can say that 0 hex 06 can also be used. So when we display the character, shift cursor to the right and ready for the next character. So these are the 3 commands that we need, or 4 commands that we need to send to the LCD before we send any data to initialize the LCD. Now, if you are writing these commands or initializing LCD before you do anything else, there's one thing that we need to be careful over here. After we power up our microcontroller, AVR, we need to wait at least 15 milliseconds. We need to wait 15 milliseconds so the AVR powers up and it's ready to go, and then we initialize LCD. Or if you are having another functions before your initialization of the LCD, that will not be any problem. So once we are done with initialization of the LCD, the next thing to do is to send these commands to the LCD. So how are we going to send these commands? Let's say send any commands to LCD. How are we going to send these? Again, I am gonna go back to the beginning of the chapter to this table, because now we need to configure the bits or the pins of AVR to send these values to the LCD. So first of all, we need to set the register select. So as we are going to send these commands, we need to select the command register. To do that, we need to set RS to be 0. So that's our first bit that we need to set. Then, as we are writing onto the LCD, the second thing that we need to do, the RW bit is going to be also 0. Let's write comments as well. 0 for comments and 0 for write. Now, then what we do, we put the comments. We put the comment number, and this is actually from D7 to D0 to D7 data pins, and that's actually going to be send it to the LCD. Now, next page. So for a short amount of time, we have to enable the latches in LCD. To enable the latch, we have to set the enable bit to be 1, and then we'll have a short delay, and then we have to set it to 0. So we need to have a short amount of high to low pulse. So 4 is going to be enable is going to be 1, then 5 is going to be the short delay, and then 6 is going to be enable equals 0. So small amount of high to low pulse, minimum 450 nanoseconds. Then we need to wait 100 microseconds so that LCD module runs that command. And then we can go back to step 3. Step 3, we put a new command, we enable the latch, and we send it again. So it just loops until we complete all the commands that we have. Now, the third step in LCD interfacing is to send data to the LCD. So how do we send data to the LCD? It's similar to what we have done. So first we say RS bit is going to be 1 in this case because we are selecting the data register. Then RW, again we are writing onto the LCD. So let's say 1 for data and 0 for write. Now, on the third step, we put the commands onto data bits. So again, D0 to D7. And then step 4, what we have done over there, we just need to repeat it again. So that's going to be step 4, 5, 6, and 7, and then we repeat again. So these 3 steps, initialization, sending commands, and sending data, has to be performed when we are doing any LCD and AVR interfacing. And this is the way of programming an LCD. So now, if we go back to our slides, it says write a C code segment that displays H on the LCD where the cursor is located. Now, as you can see, the port B of AVR is used for the data pins, and port A is used for the control bits of the LCD, like enable, read write, and register select. Now what we need to do, we want to display H on LCD. That means, and we just need to write a C code segment. We can skip the configuring LCD now because it's not saying that use this configuration. So we just want to send the data. So to send the data, we can just use these steps as a C code segment. So for example, for port A, bit 0 is enable, port A bit 1 is write, read and write, and port A bit 2 is register select. Now then we can say that for the register select to be 1, we can write a command and we can say port A bit 2 is going to be 1. Then we repeat the same thing for RV, port A bit 1, it has to be 0, so we set that one as well. And then we put the value of H onto the port B. Then what we do, we enable the latch for a short amount of time. So we set port A bit 0 to be 1. Then we add a little bit of delay in between. And then we set it to low. Then we wait 100 microseconds. So you can see the C code over here. Bit 2 is set to be 1 for register select. Bit 1 is set to be 0 for write operation. Then port B loaded with the value H. Then enable latch, short amount of delay, and then disable the latch, so high to low pulse. And then we have got 100 microsecond delay. So this is pretty straightforward C code segment that we can use in AVRs to program it. Now I'm going to show you more detailed example for an AVR, but before that I want to draw a simple block diagram for it. So it's similar to the one that we have seen in the slides, but I just want to repeat it. We have got the AVR and we have got the LCD. So 8 bits, 3, 4, 5, 6, 7, 8. So 8 pins from D0 to D7 is connected to, in AVRs, in this case is, if you are considering that one, is port B0 to port B7. Now these are going to be used for port B, and we also have the register select, read write, or enable bits, and they are on port A. So register select is bit 2, and 0 for enable. And we can use this configuration to load a data and the commands onto the LCD. Now let's go to the coding part and see how we can code this up. So before we start, I already written these down because for port B, which is going to be the data port, I just set LCD data port, and DDR LCD DDRB, and then the pin B is LCD D data pin. So port B is just used for data, and for the commands, port A is going to be used for commands, and DDR-A for LCD command DDR, and pin A is LCD command pin. And for RS, RW, and enable, I also initialize the bits that are interested in this case. And those are, so bit 0, I think it should be other way around, bit 0 is enable, so this is going to be 2, 1 and 0. So enable is bit 0 in this case. And now we have initialized the stack, and then what we need to do, we need to initialize the LCD. So we are going to write the commands together now. So what do we need? We need LDI R20 0 hex FF. This is for data port to be an output port. So out LCD, so data DDR is going to be R20. So we can say that as a command, LCD data port is output. Then we repeat the same thing for the command, because that has to be output as well. We are going to write on them. So command DDR is going to be R20 as well. That means LCD command port is output. So the next thing to do, we have to clear the latch as well. To clear the latch, we can just use CBI LCD command port LCD enable. So we are going to clear the bit 0. So this will clear the LCD's enable bit. Then, as we don't have any other functions over here, I can just call a subroutine called delay. You can create that subroutine. 2 milliseconds. I'll wait for power on. So once we powered on, we need to initialize now. So as we already said with the initialization, I'll go back to the commands table. So in the command table, as we already said, we need to set it for 8-bit data length. To do that, I'll just say LDI R16 0 hex 38. So we can init LCD 2 lines 5x7 matrix, and so on. And this has to be send it as a command to the command register. Now for the command register, as we already said, RS pin needs to be 0. So what I'll suggest you to do, if you want to write something for LCD, use a separate subroutine for command sending and use a separate subroutine for data sending. So over here, I'll just say call, and let's say the command write, which I'm going to create a subroutine to write the commands on LCD. Let's say call command function. Then I repeat the same thing, but before that, again, put a short amount of time so that it sends that command and we are ready to for the second one. And the next command is LDI R16, so hex 38. Then we can send display on cursor on, so 0 hex 0E, and then again we call command write, and we send that one. Again we call delay and we wait another 2 milliseconds for the next roll. And the next command is, as we already said, we need to clear the display screen. So LDI R16 0hex01 clear LCD. Again, call command write function so that we can send that value as well to the command register, and then we call delay 2 milliseconds again. So now we have got the third command that we need to have, and the last one is, after displaying a character on the LCD, shift cursor to the right. So LDI R16 0hex06, let's say shift cursor right, and then again this is a command, so command write, call command function. Then once we are done with command write, again call delay 2 milliseconds. So now we have got the commands and the waits for each of them, and we sent all the commands, which we are going to write a subroutine for command write. The next thing to do is the data write. So I'm just going to skip one line. For the data write, it's similar to the command write. What are we going to write? Let's say LDI R16 character H. So display letter H, and then we call a subroutine for data write. So I can say data write okay, and then another one LDI R16 I, and display letter I in this case. Again we call data write command. So now we have got the commands sent and the data sent, and we can just use here jump here, and we can just wait over there. Now the next thing to do, we need to write the subroutine for command write and data write. You can also write the subroutines for delays, but I'm not gonna consider it over here because most important for us is the command write and the data write. So let's start with the command write subroutine. So with the command write, we want to send the data to the data port. We can say out LCD data port, and we have got the value R16. So we have got the value hex 38, for example. When the command function is called, that 38 will be copied into the data port of LCD. Okay, now let's say LCD data port equals hex 16, R16, not hex 16. Then RS, as this is a command, RS pin needs to be 0. So we can just say CBI LCD command port LCD RS. So RS is equals 0 for command. Then we repeat the same thing for RW and enable, LCD command port again, LCD RW, and this is RW is equals 0 as well for write. Then the last one is SPI, because enable needs to be high for a short amount of time. LCD command port and LCD enable, and that is going to be enable should be 1. Then again, as we already said, we need to have a short delay. I can write a function for it, so I'm just gonna call short delay over there. And after the delay, I just need to clear the enable bit. So LCD command port, LCD enable. So we said enable is equals 0 in this case. So we are having high to low pulse. Now, once we have done that, we enable it. All we need to do is call delay, another delay function, 100 microseconds. We need that to send the command to the LCD and LCD process the command. So wait 100 microsecond, then return. So this is the command write subroutine. So we can use the subroutine to send the commands to the LCD. Data write subroutine is exactly similar to what we have done. So I'm just gonna copy that and write it over here as data write. The only difference is RS pin over here has to be 1. So rather than CBI, we will have SPI. So we set the RS pin. And RW is still 0, then enable is 1, then 0, and the rest is same. You can also write a subroutine for the short delay, or delay 2 milliseconds, or delay 100 microseconds, which we have seen it in the previous chapters, and I'm not going to cover it over here. So that's a pretty good example of how we can configure 8-bit version of the LCD, and we can also do the same thing for a 4-bit. So for the 4-bit version, rather than writing hex 3.8 over here, if we go from the slides as well, we need to write 33, 32, and 28 in hex in the commands first. And this will set the LCD to be in the 4-bit mode. And once we are in the 4-bit mode, what is actually do, if you want to send data with the 4 bits, you first send the 4 most significant bits, and then once that is sent, you swap the most significant with the least significant 4 bits, and you send the another 4 bits to the LCD, because we are always using D4 to D7. Okay, you have to be careful over there. And the other thing about the LCD is changing the fonts. So as we said, the character generator RAM is used to store a font for 8 characters. So to change the font, we actually have the row numbers over here for character 0, 1, and it goes. And for each row, we can actually say if it's going to be 0 or 1, and we can display a character over there. So for example, R is displayed here. And based on setting up a different ones, only the 8-bit, or if we start from 40 to 47, the last one is not used, and for 8 to 4F, again the last one is not used, but the rest can be used to define a different types of characters. And we can use these characters in our LCD. So for example, to change a row of a font, you should follow the directions as set. So first we set the cursor position to the position in one of these locations. And again, the CG RAM and the data RAM, data display RAM, are using the same cursor. So the important thing over here, as they're using the same cursor, on the command window, first you have to change the cursor position to CG RAM, perform the modifications over there, and once you are done, you have to change the cursor position back to the data display RAM. This is important, otherwise you will have a problem. And we can select the row, and by changing the bits zeros to ones, we can edit the fonts over there. So if you want to change the fourth row of character hex 1, what should we write to the command register? So the fourth row of the character hex 1, 2, 3, 4, fourth row is 4b. So in the command window, we have to say that we want to change the value in 4b. So 4b can be highlighted and we can change using the command register. And this is the end of LCD part of this chapter. If you have any question related to the LCD, note them down and you can ask me during the question and answer session. The next thing that we are going to cover is bounce issues. So on the embedded development boards or in embedded systems, we are using mechanical switches or mechanical push buttons. So what is happening is, when you push a button, as this is a mechanical button, you are not gonna get ones or zeros exactly at the time that you want. So what is happening over there? We start to see, okay, 1, 0, and we start to see some fluctuations between ones and zeros on the electrical signal. This is actually a bouncing issue. That means we are not having the valid values over there and it's just fluctuating. So we can say that when we have the button and we measure it over a time, you will see that bouncing, the fluctuation on the button output. Now the microcontroller has to deal with that. Why? Because microcontrollers are faster than that switch and it can read each of these values one by one. Okay, because let's say the microcontroller has got maybe or the button has got a 10 microsecond bounce, and the microcontroller can easily read that bounce. So what we generally say is, doesn't matter if it's going to be the same manufacturer, same button or something like that. It actually depends on how much force you apply and how fast you press that button. And we can have a bouncing periods between 1 to 5 milliseconds. So what we can see about this non-ideal behavior is that as it generates a multiple transitions, the microcontrollers has to deal with that. And there are a couple of ways of dealing with bouncing issues. We call it debouncing switches. So to have a debouncing switch, you can either use a analog filtering, which is an RC circuitry. In RC circuitries, capacitors actually filters the instant changes in the switching signals. So we will have valid zeros and ones all the time. Or we can use a digital gates, the latches. So generally SR latches, SR flip-flops are used over there, and whenever switch is moving between the contacts to create the bounce, the flip-flops are maintaining the output at 0. So when the 0 is fed back from the output, you have a stable operation over there. Or another alternative is, we can have a software debouncing. We can create a delay loop, which is a quite common for the bouncing switches, and we can create a delay in a delay loop and we can overcome this issue. But the only thing that we need to be careful with the software debouncing, that if you have a lots of debouncing over there, you need to keep delaying it. So this will cause the microcontroller to wait over there for a long time. So imagine if the switch is debouncing forever. That means you are holding, you are keep waiting for your microcontroller to perform that debouncing issue. So we have to be careful on how are we going to deal with debouncing of the switches. And this is just an example, a software example showing loops for debouncing. So the next thing that we are going to consider in this chapter is the keyboards. Keyboards are one of the fundamental input peripheral for embedded systems and microcontrollers. But if you allocate a normal keyboard, you are going to use all the pins of your AVR, which is not possible. This is not the way of implementing it. And with the ordinary PCs, this is actually solved by they have a different separate microcontroller for the keyboard that deals with all these key presses. And in embedded systems, we have got a keyboard something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0, OK, cancel, up, down, right, left. And each of these buttons are connected with an array of switches underneath. So you can see the switches, they are connected to the VCC line. So when you want to read these now from the columns, you are going to see high values. They're all ones because they're all pulled up to VCC, high voltage. And we all got the rows are going to be connected on some part of the AVR. So we can say that the rows are going to be inputs and the columns are going to be outputs that we are going to read. Okay, so we will force an inputs on these rows and we will read the outputs on the columns. So how it is going to be connected? This is just showing that we can just use one port of the AVR to have a 4 rows and the 4 columns decoding over there. So how are we going to decode the keys? There are 2 steps in the keyboards. One of them is the key press detection, another one is the key identification. So the key press, we have to find out if any key is pressed, and key identification, we have to identify which key is pressed. So to do that, the microcontroller has got a strategy for that. So what we do, as these are going to be the inputs and these are going to be the output, you can use the different ports, you can use the same ports, it doesn't matter. What we do, we set these all as ground for press detection, and for identification we set them all to high, and we can check one by one what is going on. So now, as they are all grounded, we go one by one and check individual line if there are any key is going to be pressed or not. So starting with the first line, we have got some keys pressed over there. So that is pressed, that's not pressed, pressed, not pressed. So what we are going to see over here on the first row, as this is connected now to the ground, we are pulling this line D3 to be 0, and we are also pulling this line D1 to be 0, and the rest are 1. So we are going to get 0, 1, 0, 1 on the D3 row. So we can read that from D3 0, 1, 0, 1 down as an output on the port B in this case. Then what we do, we jump to the next one and we checked that row. We put it to ground. If the key is pressed, we can see that this is going to be 1, 0, 1, 1. So only one key is pressed. We are going to see 1, 0, 1, 1 on this one. Then it scans the next row. Then it sets that one to do 0. So that is not pressed, that's not pressed, that is pressed. So that's going to be 1, 1, 0, 1 on the output. And we scanned the third row. Then the last one, we set that one to the ground and we scan that one. There's no, the keys are pressed. So we'll just have 1, 1, 1, 1 on that end. So we can easily read and identify which key is pressed by using this algorithm. So we start from D3, we set each of these rows to 0, the ground, and we can check if there is a short circuit or not, and we can identify which row and which column is the key and pressed. So example says, write a function that waits for a key to be pressed and then returns the code of the pressed key. So we know that we have got the array of switches underneath of that keyboard. we can easily write a algorithm for it. And that algorithm is pretty straightforward. Ground all rows, read all the columns. All keys are open. If not, start again. If yes, go to the next step. Read all the columns. Is there any key down? If it is no, carry on reading the columns. If it is yes, wait for the debounce and then read the columns. If this is a valid press, then if the key is down, go to the next row. Otherwise, go back and read the columns again and carry on with these steps. So if the key is down, we ground the next row, read the column, the key press in this row. If yes, find which key is pressed. If no, go back and start again, get code from the table, and that's it. It's pretty straightforward actually. You just need to ground and check, ground and check, ground and check. So this is the end of this chapter. If you have any question related with the LCD, switch debouncing or the keyboard interfaces, note them down and you can ask me during the QA session. Thank you.